So my topic is polynomial hierarchy. So before everything gets started, I would like to talk about the notion of polytime relation. It is defined as this. A relation R is called polytime relation if and only if there is a verifier V or a Turing machine can decide it in polytime. And I'm gonna say that you can describe NP by the polytime relation with only one variable y1, which is the base case of the relation. But why is this though? Remember during the class, we defined the NP by the guessing and checking trick. We non-deterministically guess an instance and check it in some polytime. And I'm gonna say we can describe this guessing and checking trick by the relation. So it is something like this. So there's a language L is in class of NP if and only if there exists a y1 such that the relation of x and y1 holds. But why is this so? I'm gonna provide a solid example on next slides. During the class, we learned that the set problem is an NP problem because we non-deterministically guess a truth value assignment and verify it by plugging it into the Boolean equation in polytime. Here, the same thing, we can think about the y1 is the truth value assignments, and x is the Boolean equation. So the relation R holds if and only if there exists a truth value assignments y1 can satisfy the Boolean equation x. The similar thing for co-NP. Remember the co-NP is the complement, the language complement of NP. So for here, instead of using the existential quantifier, we're gonna use the universal quantifier because the complement of the existential is universal, and everything else is the same. It is saying that for all y1 such that the relation holds. I think it is time to talk about the polynomial hierarchy. Actually, we just saw the first level of polynomial hierarchy, which is NP, and it is defined as exists some y1 such that the relation holds. We denote it as sigma 1. For any other level I, we can define it as exists some y1. For all y2, exists some y3 up until some quantifier yi such that the relation holds. The quantifier is existential if the I is odd, otherwise I is even, then it is universal. The meaning of the yi, we can think about the set problem. So each yi is a polysize vector of Boolean variables, which actually is the truth value assignments. And the definition of the polynomial hierarchy is the union over all the levels. The co-NP is the similar thing, except we denote it as pi, and we also flip the quantifiers in front of those variables. It is because the De Morgan's law. We just saw the base case, the first level of polynomial hierarchy, which is sigma 1, and it is NP. And by the definition, we can enumerate the second level, the sigma 2, which is there exists some y1 for all y2, such that the relation holds. But what does this really mean? To really understand the second level of polynomial hierarchy, I would like to talk about the language in the second level. It's called maximum independent set. It describes given a graph G and K, the largest independent set in graph G has exactly the size of K. I mean, if it is the case, you can think about there's a subset S in graph G. The S is independent and has size K. But not only this, we also need to satisfy that for all other subsets in G, we denote it as S prime. Those S primes is either has size lesser than K, or S prime is not even an independent subset. So it gives an intuition that we can treat the y1 as the s and the y2 is the s prime. So it is saying that there exists some s which is independent and has size k. Also, it needs to satisfy for all the other subsets S prime. The size of S prime is either lesser than K, or S prime is not an independent set. So to really verify the maximum independent set, we need to not only guess one set S, we need to guess a lot of set S and check whether if those are independent. Among those independent subsets, and we check whether the largest one has size K. So, and remember that the independent set problem is NP problem, which means we need to solve a lot of NP problems. We need to solve NP problems a lot of times to really verify the answer. So it gives us the intuition that this problem is at least as hard than NP. So it gives us the intuition of NP's NP, which means you need to solve a lot of NP problems to really decide it. We normally denote it as the NP to the power of NP. It means we solve some NP problem non-deterministical times. So like in the previous example, we solved the independent set problem non-deterministical times, and to really decide it. So here is the diagram for polynomial hierarchy. The first level, as we talked about, is NP and co-NP. The second level is NP to the NP, which is we also solved, and we have a co-NP to the NP. And we do have a zero level, which is P. Why is this though? Remember the polytime relation R is the relation that there's a Turing machine can decide it in some polytime. Where since in the zero level there's no any variable yi's, which means there's only the relation of x, which means we have a Turing machine can decide it in some polytime, which is exactly the definition for P. Also, here are some trivial property for polynomial hierarchy. For each of the lower level, it is the subset of the upper level. Also, it is a subset of the upper level in the other thread. Say the NP is the subset of NP to the NP, and NP is also the subset of co-NP to the NP. The similar thing for co-NP. So far, we have the relation here, where the P, the level 0, is subset of NP, which is the level 1, which is the subset of level 2, and subset of level 3, and so on and so forth. The entire polynomial hierarchy is the subset of P space, and P space is the subset of exponential time. So we have the chain of the relation here. And we do have the the collapse on polynomial hierarchy. So it is saying that if the some sigma 1 for some level I, if the sigma I is equal to pi I, then the polynomial hierarchy will collapse into this level. So you can imagine the base case gonna be if NP and co-NP, then the entire polynomial hierarchy will collapse on the level 1. And I'm gonna talk about the Karp-Lipton theorem a little bit. The Karp-Lipton is basically the collapse on level 2. The Karp-Lipton theorem says that if we can solve the set problem in polysize circuit, then the level 2 collapse, which means the entire polynomial hierarchy collapses into the level 2. But we generally believe that this kind of collapse is unlikely, which implies that there's no polysize circuit can solve set problem or NP problem in general. Thanks for watching. Feel free to ask any questions under discussion. And here are my references.